Welcome to class number 8, session number 3. In this session, we will discuss improvements in sensitivity for metal oxide sensors upon decreasing one or more of the characteristic dimensions of the metal oxides to around 10 to 20 nanometers. Let's start with the dilemma of thin film metal oxide gas sensors. For dense structures, surface interactions with the gas phase affect the conductivity of only at the top of 10 or 20 nanometers. Therefore, it is reasonable that making these films ultra-thin lead to high sensitivities. At this point, please note that the depletion length can be increased by selecting materials with a high dielectric constant or by reducing the trap concentration in the film. However, in practice, this situation is much more difficult, either because it is difficult to control the purity of the film or because there are other factors that need to be taken into account other than the dielectric constant. So, what about the other option to use ultra-thin films? One option is reducing the film thickness to comparable dimensions as the depletion length, namely 10 or 20 nanometers. But in this case, stability problems due to film-substrate interactions and other adverse effects connected with the film-substrate interface become so critical that improvements in the performance are not achieved. In order to get around these disadvantages, a simple yet effective solution was developed. The solution involved thin film deposition over sacrificial microsphere templates to produce the so-called eggshell structure with high surface area and small interfacial area. The production of the eggshell structures that have high surface area and small interfacial area involves thin film deposition over sacrificial microsphere templates. With PMMA microsphere templates, it is possible to obtain 4 or 5 layers of closely packed microspheres. Metal oxide films are deposited on the top layer, and after the organic template is burned off, during the calcination step, the inorganic film collapses due to the substrate. This often results in insufficient adhesion to the substrate. Therefore, improved adhesion can be achieved by going from multi-layered microsphere templates to a single-layer template. Polystyrene microsphere suspensions in ethanol were used in order to create a single layer of microspheres, and the process details are given in the following. In the presented examples here, you can see in the left image on the screen that the eggshell structures are nicely controlled compared with the MMA templates and a monolayer of closely packed microsphere. The film after titanium dioxide sputter deposition can be seen in the right image. In another example, chemical and physical synthesis routes are combined to prepare macroporous peroxide oxide thin films by pulsed laser deposition into the PMMA microsphere templated substrates. The resultant films have a monolayer structure of quasi-ordered hollow hemispheres with high surface area, porosity, and permeability to gases. The gas sensitivity of the macroporous metal oxide films are examined and compared with the plain films deposited under the same conditions on untreated substrates. You can see here that the macroporous film are much more sensitive than the control film. This dramatic enhancement in sensitivity is attributed to the increased surface area and the decreased interfacial area introduced by the microsphere template. Please note that the inner surface of the metal oxide hemisphere is also exposed to gas phase throughout the burst holes produced during the calcination step. When you compare the gas sensitivity of the eggshell structure with the plain films deposited under the same conditions on untreated substrates, you can clearly see that remarkable improvement in the performance of the templated films. This improvement is attributed to the increased surface area and the decreased interfacial area between film and substrate introduced by the microsphere template. The present slide shows representative results on exposure of the titanium oxide eggshell structures to nitrogen dioxide at 300 centigrades. The right graph is the calibration curve showing the normalized response as a function of nitrogen dioxide concentration. From this curve, the detection limit can be estimated to be on the order of 250 ppb. This is better than most results one can achieve or find in the literature, certainly for titanium dioxide sensors. But it is not quite enough for practical applications, since for environmental protection, you want to measure concentrations as low as 50 ppb, which is the nitrogen dioxide concentration in the clean air. The third generation of the metal oxide sensors is based on nanowires, as explained in the previous sessions. Metal oxide nanowires are crystalline structures with a precise chemical composition, surface terminations, and dislocation defect-free. The nano-size dimension generate properties that can be significantly different from their coarse-grained polycrystalline counterpart. Surface effects appear because of the magnification in the specific surface of nanostructures, leading to an enhancement of the properties related to that, such as catalytic activity or surface adsorption. Properties that are basic phenomenon underlying solid-state gas sensors are achieved and discussed. The use of metal oxide nanowires as gas-sensing materials should reduce instabilities suffered from their polycrystalline counterparts, which mainly associated with the grain coalescence and drift in the electrical properties. These sensing nanocrystals can be used as resistors or in FET-based or optical-based gas sensors. An example of nanowire-based metal oxide sensor is based on zinc oxide, as shown on the screen. Zinc oxide with a band gap of 3.37 electron volt is a promising semiconductor material. In particular, one-dimensional zinc oxide nanowire have promising application as gas sensor due to their remarkable physical and chemical properties and the structure resulted surface-to-volume properties. In the example presented on the screen, well-aligned single crystalline zinc oxide nanowire arrays was synthesized on a silicon substrate using the chemical vapor transport and condensation method. Comparing to other techniques, it's quite simple and novel method. It utilized only silicon substrate and popular inorganic material source, thus making this approach quite promising for the production of nanowires of metal oxides for getting high sensitive sensors of metal oxide. Another example on the nanowire-based metal oxide sensor is presented on the upper side of the current screen. The presented example focused on the measurement of the sensitivity of tellurium dioxide nanowires in terms of resistivity. The resistance response of the tellurium dioxide nanowires are measured from synthetic air to 10, 50, and 100 ppm nitrogen dioxide gas at room temperature. Since the tellurium dioxide is p-type metal oxide, the sensor's resistance decreases upon introduction of the oxidizing gas. And also, the sensor's resistance increases when exposed to reducing gas, such as hydrogen disulfide. As could be seen on the screen, the response time of the nanowires in this case is about 2 minutes. In the bottom side of the screen, you can see another interesting behavior, sensing by N-type iron oxide porous thin towards H2S. As seen in figures C and D, the response for 10 ppm of hydrogen sulfide, or H2S, changed from N-type to P-type with an increase in the working temperature. Below 300 centigrades, the sensors show N-type response, while at temperatures above 350 centigrades, the response is P-type. These results clearly indicate a switching from N-type to P-type behavior with an increase in the working temperature. Similar response behavior is observed in some other reducing gases, including ethanol, methanol, and acetone. However, the maximum N-type response for hydrogen sulfide is seen at 250 centigrades with a response and recovery time of 5 seconds and 10 seconds respectively. Another example for nanofiber sensors that are made of semiconducting metal oxides is presented on the screen. In this example, a typical electrospinning procedure was used to fabricate the nanofiber titanium dioxide gas sensors. These sensors operate at elevated temperatures of around 300 or 400 centigrades, where gas adsorption and desorption processes modify the surface conductivity. The sensitivity of 4 sensor prototypes comprising titanium dioxide nanofiber mats has been tested against traces of nitrogen dioxide, carbon oxide, hydrogen methane, and diethyl methylphosphonate vapors in dry air at temperatures between 100 centigrades and 400 centigrades. Please note that nitrogen dioxide and carbon oxide are toxic pollutants. Also, please note that hydrogen and methane are potentially explosive gases, and the DMMP serves as nerve gas simulant for development of detectors for chemical warfare agents. Representative results of the resistance response of one of the sensors upon cyclic exposure to nitrogen dioxide at different concentrations and temperatures are shown in the figure that is presented on the slide. In general, the resistance increases for the most part in monotonic way with nitrogen dioxide concentrations of 500 ppb to 12.5 ppm. The histogram's shape results from the competition between slow kinetics at low temperatures and enhanced desorption at high temperatures. At 300 centigrades, the resistance increases by 833% when the sensor is exposed to only 500 ppb nitrogen dioxide. In summary, metal oxide-based sensors are promising candidates for gas sensing application, especially for applications that require high temperatures. Yet, many challenges are still exist, and the field is under development and research. We come now to the end of class number 8. Thank you for your attention.